All right, next what we have. All right, exothermic and endothermic reactions, we've talked about those already. We have equations with them. Now we've written chemical equations before. All right, this time what we're going to do is add energy to it. And so I have a chemical equation we're going to put up here. Now you've just seen this video. This is a thermite reaction. So we have Fe2O3. There's our iron oxide plus 2 aluminum will give us aluminum oxide plus iron. Now, hopefully you remember this is an exothermic reaction, lots of energy coming out. So there's a couple ways you can write this. First way, they might show you this. They might show you delta H is equal to, if you remember this is enthalpy, really for purpose of this class is energy, okay? So the energy is equal to, well if it's exothermic, what they'll do is they'll write this as a negative number. So for this one it's negative 849 kilojoules per mole, okay? So this is one way you can write it. You write the whole entire equation, then you go delta H equals negative 849 kilojoules per mole. This is what we do for exothermic reactions. Why do they write this negative? Because exothermic energy is leaving. So we're losing energy if it's exothermic, so it becomes negative. So this is one way to write it. Now you can also write the same equation out, except, here we go, so there's our iron oxide plus our aluminum, giving us aluminum oxide plus our iron. So the other way you can write it is you can actually put energy in the equation. So I'll put my 849 kilojoules per mole right here. Now, why did I write this on the product side? Well, this is what's being produced. It's going out. And so I'm going to write this on the product side. You don't need to write it as a negative number right here if you put it in the equation, okay, because the product is given off. So you can write it, I'll split them up. So you can write it as this, all right, where you can write your equation with delta H equals, if it's exothermic, it's negative 849 kilojoules per mole. Or you can write it as the product. Now, if it's endothermic, here's the only thing that will change. If it's endothermic, delta H would be positive. And if it's endothermic, and I write it in the equation, we don't write the energy on the product side, we write it on the reactant side. So if it's endothermic, delta H is positive, and the energy is written on the reactant side. All right, so we've already looked at this graph here. Let me draw it real quickly. Where we had temperature and we've had energy. And so as you're heating an object up, it'll heat up. Let's say it's a solid first, it heats up, and then it'll start to melt, and then it'll heat up again, then it starts to vaporize, and we heat it up again. So we've already looked at this basic drawing right here. So we had our lovely solid, our liquid, and our gas is changing temperature. Right? This is where it changed states. Okay? You should definitely know if it goes from a solid to a liquid. We call that, what do we call that again? No, that's right. Hopefully you said it. We call this melting. When it goes from a liquid to a solid, we call it freezing. All right? Right here, when it goes from a liquid to a gas, we call that vaporization. Gas to a liquid, we call it condensation. Okay? So that's where it is on these graphs. If you look at these graphs, okay, if you're going this way on the graph, so you're going up this way and you're going this way, so if I'm graphing this and this is what it's doing, it's starting to increase, okay, we're taking in energy, okay, energy is coming in. So all of these processes, okay, if energy is coming in, are endothermic, okay, so energy is going into them. So to go from a solid to a liquid, energy has to come in to melt something, so it's endothermic, okay, that's the processes. And there's the bell. If energy is going the other way, meaning we're up here on the graph and we go the opposite way, it means energy has to come out. Going from a gas to a liquid, energy comes out. Liquid to a solid, energy comes out. Going down this way would be, if it's going out, we call that an exothermic process. Now there's a second graph I want to look at. Now it's this graph right here. All right? Now, this graph works a little bit differently. All right? And I'm going to label some parts of this graph and show you some things here. I'm going to expand this just a little bit. Okay? So this is also a phase change graph. Okay? So we're still looking at changes in states. Okay? So it's changed states. But our axes are going to look a little bit differently here. Okay? So our axis is going to look a little bit differently here. We're actually going to put temperature down on the x-axis. Okay, so temperature is going on the x-axis. We're actually going to put pressure on the y-axis. Okay? Now I'm going to put this in, I like to put my units, I'm going to put this in atmospheres. Okay, I'll put this one in degrees Celsius. Alright? Now I'm going to use a substance that you're familiar with, alright? But you'll have different graphs. No matter what the substance is, it'll have the same basic features. What I'm going to just use is, we'll say, liquid water. Okay, so we're going to use water here. All right. So we're going to say this is 1 atmosphere here. All right. 1 atmosphere is basically if you went down to the beach and stood on the beach and at sea level is 1 atmosphere of pressure over you. We'll talk about pressure later in the year. All right. And we'll say, let's see, let me look at some parts of this graph. That probably needs to be 0 degrees Celsius right about there. Say it's 100 degrees Celsius right about here. So in this graph, let's say I had ice and it's really, really cold ice, so we're right here. Right? If I start to heat up liquid water or solid water or ice, so this is the area for a solid. Okay, so A is going to be the solid area. Okay, so it starts to get to this point right there. What's going to happen is we start to melt. So there's what it is on the graph. Okay, in this section here, we have a liquid. Okay, we know as we keep heating it up, we increase the temperature, keep heating it up, and oops, this is a little bit off. If we go way down here, oh, that's close. All right, at 100 degrees Celsius, what will happen to water? Well, it starts to vaporize. This big section here for C, this is a gas. So I keep on raising the temperature, and boom, there it goes. Now, this graph's a little different because it's not just temperature and energy, it's temperature and pressure. Here's some fun things you can do with water and with pressure and stuff like this. It's kind of cool. So what can you do? Well, let's say we lower the pressure on this. So let's go down some. So same temperature, we lower the pressure some. If we lower the pressure, look what's going to happen. All right? The temperatures at which they melt and the temperatures at which they boil start to change. Earlier this year, I told you that I'm going to boil water at room temperature. So what am I going to mess with? I'm going to mess with the pressure. Okay? And as you start to mess with the pressure, you can actually change states of chemicals based on not just temperature, but pressure. Okay? So different pressures can affect it. Some of you might have a pressure cooker at home. What do pressure cookers do? Well, it allows you to have liquid water at a higher temperature so you can actually cook your vegetables or whatever you have in your pressure cooker at a higher temperature. How? Well, if you increase your pressure, look what happens to your new boiling point of water. It's way over here. So it's actually past 100 degrees Celsius. It might be like 120 degrees Celsius or something like that. Okay? So you actually increase the pressure in a pressure cooker. Now, there's a couple points to look at on this graph. This point right here is known as the triple point. That's triple point. The triple point's kind of cool, all right? No pun intended. All right, what we have here is this substance can exist as a solid, a liquid, and a gas. All right, it can exist as a solid, liquid, or gas depending on the energy that's in it. So at some point in time this year, I'll try to show you the triple point and actually be able to see that. If you can imagine a gaseous slushy. Right? You got your liquid, got your solid, got your gas at the same time. All right? There's another bell. So this is just another phase change diagram. I guess one more point to show you. This is called the critical point. As you can see, as you increase pressure, we can heat up the liquid higher and higher. There's a point at which the liquid, doesn't matter how much pressure you put on it, it's going to become a gas. Okay? If you raise the temperature up enough, doesn't matter what your pressure is, it becomes a gas. They call that the critical point. All right, so that's the basics of this graph, and if you have questions, we'll talk about it more in class.